what I think is the most important text from what I wrote the last time, that you have t is some function that denotes the worst case runtime, b denotes some kind of benchmark function, and the O, omega, and theta are ways of comparing your runtime to a benchmark, right? And the comparison is done what's called asymptotically or in the limit. And there are sort of three situations that need to be considered. The limit is less than infinity, that's big O, the most common thing that you see. If the limit is greater than 0, it's omega. And if the limit is a constant which is not equal to 0, theta. So I often get the question do you need to memorize this or know this for any test? Well, technically, you don't need to know these definitions. You can survive without them. But we are going to be doing big O notation a lot during the course and for some of the final tests. So for that, you need to understand what it means, and this is sort of the understanding that you have. OK. And at the end of the last lecture, we considered sort of now, we're sort of stepping away from the math and going to a specific application. Consider a linked list L. How long, or what is the running time? And I should say, in running time here, I mean worst case running time. So what is the worst case running time to find an element in the list? So where T of n denotes the worst case running time of find. Someone had their hand up? No. OK. So, and what we get is that T of n is theta of n. What this means is it is O of n. It's at most n. It's also at least n in the worst case. So this is important. Omega does not mean best case. Omega is a lower bound on the worst case. You're always looking at the worst case, and you're trying to pin down how long it takes. So for the worst case, you give an upper bound and a lower bound. Does that make sense? OK, so I want to sort of talk about this a little bit more, giving another example. But are there any questions about this? OK. All right. So what I'm going to give to you now are two sorting algorithms, which you may have seen before. So let's consider the problem of sorting an array of n ints. Right? Classic problem. How many of you have seen an algorithm for this? Okay, some of you. Any suggestions? What algorithms do you know for this? Yeah? Merge sort. That's a fancy sort. What's the dumbest, simplest algorithm? Yeah? Insertion sort, bubble sort, selection sort, Bogle sort. Bogle sort is actually probably more complicated to code than the others, but yeah. So selection sort, I don't know. I think Bogle sort just means that you randomly permute until you eventually hit the right solution. So to me, selection sort is conceptually the simplest sorting algorithm. So let me tell you what selection sort is. So A is an array of ints. So selection sort, the idea is to find the min of A, swap with A0, so move it to the beginning of the list, and then just sort of find the min of A going from 1 to n minus 1. So in the remaining elements, swap with A1, so on and so forth. This algorithm is called selection sort. Okay? So let me just write out some code for selection sort. And now I'm going to be more sort of careless with my syntax. I'm going to mix sort of a bit of Python and C, because I don't want to write the for loop conditions using semicolons and the exact thing. So I'm just going to write something like, say, for I going from 0 to n minus 1. Right? This is like the length of the array. So n is the length of A. So we're going to start with the current min, which is AI, and the index of the min, which is I. Right? So this is saying that I starts over here. And then we'll go j going from I to n minus 1. So j is going to range over all the remaining indices. And so what you're doing is simply finding the minimum in j, in this inner loop. And you initialize it to the ith element. So you say if a of j is less than the current min, then we'll just set the min being a of j and the minimum index being equal to j. And yeah, so this is it. Right? So what this loop is, oh wait, I have one more thing to do, sorry. So I have to write the final thing. I'm just going to write this out in English. I'll say swap a of the minimum index with a of I. Does that make sense? So this loop j, it's going to go through all of this. It's going to find something in the end. So this is going to be the min index. It swaps these two, and it increments I. Yes? So hopefully nothing is, like conceptually, this is the logic that's just finding the min. The loop is just going over all the j's to find the minimum. And then once you find the minimum, you swap it with the I. Right? So this is selection sort. So there's insertion sort, which as we talk further, we'll see is actually, it's a better algorithm. So insertion sort is kind of different in the sense that, so note that in both of these algorithms, so let's say here at I, this portion over here is already sorted. Right? So in selection sort, this initial portion is sorted because it's the first I minimum elements. And then you find the next one and you swap, so on and so forth. Here, what we're going to do is we'll say, suppose this is sorted. Instead of trying to find the next element to place, let's just place the ith element by swapping. So instead of the second loop, the j going this way, the j is going to go this way. Does that make sense? So you look at AI, and you'll say, keep swapping until AI reaches the right position in this part. Okay, so it actually ignores everything beyond, whereas selection sort loops over the whole thing each time. Okay, so I'll write out the code for selection sort. So this is for I going from 0 to n minus 1. The code is even simpler. So we'll initialize j is equal to I. I'll say while a of, while j is greater than 0, and make sure I get my indices right, aj minus 1 is greater than a of j. We'll swap aj minus 1 with a of j. Okay? Is this clear? So what this is doing is simply it's saying that j is now ranging from here. J starts off, and then I have to decrement. I'm sorry, yes. And then j minus minus. So j starts somewhere. So let's say j starts at I. If AI minus 1 is greater than AI, if this element is larger, then swap these two. Then start from here and try to swap these two. So it's just trying to repeatedly swap until AI will reach the right position. Is that clear? Okay, so these are two different sorting algorithms. And the Bigot notation can be used to try to compare them to each other or with respect to a benchmark. All right. So let's say T of n is the worst case running time of selection sort. Most of you probably know what the answer is already. Right? What's the answer? You've probably heard that it's O of n squared. But let's try to figure out why that's the case. Okay? Any questions about this? So T of n is the worst case running time of selection sort. How are you going to argue about this? So the linked list was easy. It's a single loop. But how are you going to argue about this? So here's the code for selection sort. Yes? Yeah, you count an operation. So yeah, exactly. But tell me how to count them. Tell me how. Good. So okay, let's start with that. So you have to count the number of operations it makes in the worst case. How are you going to break this up into something that you can reason about? Yeah? Break it up by loops. Okay, good. So there are two loops, right? There's an outer loop and there's an inner loop. There's an outer loop and an inner loop. Okay? Now, what can you say? Yes? Why? Mm-hmm. Hey, I didn't say anything. No, okay, so you're sort of kind of there, but what I want to help you do is to formalize your logic there, right? Yes? Okay. But 2 times, why is that n squared not 2 times n? Yes? Okay. Okay, all right, good. So someone else had their hand up. Yes? Yes, so right, good. So there are 2 nested loops, right? And the outer loop goes for n. What about the inner loop? Sorry? Okay, so that's a more, right, that's a more sophisticated argument. But yes, so, but let me say that clearly the inner loop goes at most n. And O is an upper bound. So the outer loop goes n, the inner loop goes at most n, then it's at most n squared. Right? So to get the big O bound, you can cut corners. And that's sort of the whole benefit of doing the big O bound is you don't have to worry. You can say, well, okay, as you said, like, well, it's on the average, it's something. But then now, when you start doing average, you have to be careful. Are you getting an upper bound? Or it's correct. And we'll talk about that. But to get the big O bound, remember, big O is an upper bound. And again, if you can always make Bn bigger by a constant factor, and it's still fine. Does that make sense? So remember, like, we had these examples where we said, where's the example? Said like 5n plus 3 is just O of n. So when I take 5n plus 3, I ignore the 5 and I ignore the 3. I'm only looking at the dominant term in the polynomial. That makes sense? So for understanding this, what I can simply say is there are two nested loops. Right? The outer loop runs at most n times. It runs actually exactly n times, but exactly is at most. So, or at most, if it's exactly n times, it implies it's at most. The inner loop runs at most n times. Right? Sorry, someone, why? Okay, good. Why is it not n factorial? So, what you're counting is how many times each line of code is executed. Right? So how many lines of code are there? There are basically just a constant number of lines of code. It's like 1, 2, 3, 4. It's like maybe 12 or 13, depending on whether you use C or Python, it doesn't matter, right? So it's a constant number of lines, a fixed number of lines of code. Each line of code, I will argue, will run at most n square times. It's not factorial because, you don't multiply n plus 1, n plus 2. You're actually going to add them up. Because you're adding up how many times each loop runs. You don't multiply them together, right? Because you're counting how many times is this going to run. I'm going to say this entire block of code is going to run at most n times. And this line of code is going to run at most n times each time this loop is called. And this loop is called n times. Hence, this is going to run at most n square times. This line of code is going to run at most n times. So if you wanted to count it very precisely, you have to be careful. You have to say, well, this runs at most n times, and that runs at most n times, and this runs at most n squared. And you're going to count the number of lines of code. But for a big O bound, you don't have to do that. Yes? Well, yes, so we'll get there. So that we have to do big omega. If you want a lower bound, not the exact, like it's up to a constant. So let me just write this. So inner loop runs at most n times. So each line of code runs at most n times n equal n squared times. That makes sense? The outer loop runs n times, the inner loop runs n times. So every line of code runs at most n squared times. Some of them run even less. But that's why there's an at most. Right? There are a constant number of lines of code. What does constant mean? It's the number of lines of code doesn't depend on n, kind of obviously, because you write down a piece of code and it works for all n. The constant number of lines of code, hence the total running time for all inputs of size n. So let me call this constant c, some constant, is at most cn square, which is equal to on square. This, what I've written, okay, so this isn't the most formal proof, but this is like some formal argument, or it's a semi-formal argument for why t of n is O of n square. So when I ask you, when you in one of the homeworks or tests have to write an algorithm, so you write some pseudocode, you don't have to write code, and then you give a big O bound, you have to write down that argument there. Right? So the key is to say there are two nested loops, the outer one runs n times, the inner one runs n times, so each line of code runs at most n square times. You even don't have to write this, there are a constant number of lines of code. I'm writing this for your benefit. So you don't have to explicitly take limits when you're doing a big O analysis. The limit is the fundamental definition, but this is good enough. No one actually will explicitly take limits unless things are unclear. So this is what people would write to say T of n, so hence the running time of selection sort T of n is O of n squared. That's what we get. So remember, we only did at most. So we don't know if this is tight. Maybe the worst case running time is much better than n squared. Is this clear? Any questions? Yes? So the unit of time is actually the number of operations. So technically it's the number of elementary operations, where the number of elementary operations is defined by what machine you're running on. And for the machines that we deal with, each of these is either a comparison or a data move. Like you're copying from one index to another. So each of these is thought of as a constant unit of time. Because technically that time would depend on which machine you're running on. So this is a good point. The reason why big O analysis came about is because you want to analyze this algorithm regardless of which machine you're running it on. Right? And if you start thinking explicitly in time, in some machines, this might take more time than this. In some machines, the data move might be more expensive. The comparison is cheap. But what we say is we count just the number of elementary operations. Often in sorting, they'll just count the number of comparisons or swaps. Someone else had their hand up. Yes? We are, in this course, we're not going to deal with what's called the space complexity, although the space here is just linear. Because the only extra space that you need actually is just you have 4 indices, or you have 4 variables, I, j, min, and min end. And there's no other space that is used. But it's obvious, yeah, okay. So far so good. Is this clear? Okay. So, and for these algorithms, the O bound is actually quite easy to come up with. The omega is going to be a lot harder. Okay, so T of n is still the worst case running time of selection sort. And what O of n square is like saying it's at most n square. Yes?
And that insertion sort, I think, goes from n to n minus 1 to 0. If we're starting at the end of it.
No, so I will still go from 1 to n, but j decrements.
Then wouldn't
J starts from I.
Okay,
J starts at what I is. Yeah. Okay. All right. So what we did is we talked about the worst case running time being at most something. But can we say the worst case running time is at least something? Suppose I want a lower bound. This is harder to argue. Suppose I want a lower bound. So lower bound means I want to say the worst case running time is at least something. Yes?
It would be at least n because the outer loop runs n times.
Good. So it's at least n. So one thing that is sort of clear is that T of n is omega n. I won't write down the argument explicitly, but you can see that the outer loop runs exactly n times. So these lines of code here will execute at least n times. So good. So it's omega n. Can you do better? Right? So now once you get one bound, yes?
N times n half.
Okay. And why n half?
Because the inner loop on average runs through n half, because it runs like all the way at the beginning, and then at the end it just runs like one element.
Right. Exactly. So I will write this out a little bit more. I'll open it up, but exactly, you're right. So the outer loop runs n times. Now the inner loop, now this is the part that you have to be careful with, is the number of times it runs depends on what I is. Okay? So when I is equal to 0, this loop runs n, or yeah, n. When I is equal to 1, it runs n minus 1. then it runs n minus 2, and then it runs n minus 3. So you can't just say, oh, it runs at most n. And at least, well, in the smallest case, it only runs for once. So there are cases where the inner loop runs for a very small number of steps. Okay? So just for just for those who don't see the half exactly, I'm going to break it up a little bit, right? So let's count how many times the inner loop runs. Okay? So that's what I want to count the number of times. With respect to I, because it depends on I. Does this make sense? So it depends on what the value of I is. So when I is equal to 0, how many times does the inner loop run? N. When it's 1? Okay, so now I just want to check if you're all awake and following. So I'm going to give you 3 options, hence the post-its. So for the ith, what is this option? So I want you to tell me precisely, not at most at least, precisely how many times it runs. Is it going to be n? Is it going to be I? Or is it n minus I? Okay, so what is the answer? Good. It's actually funny, the kinds of things one can read, right? So not only is it that most people got it right, they raise their hand up very confidently, right? Which shows that everyone follows. Usually otherwise, like even if like slowly people will raise it as if, something's going to happen if they get it wrong. So good. So I think everybody follows. And so when I is equal to n, which is the last iteration, or I guess technically n minus 1, then the number of times this runs is 1. So this is exactly how many times it runs. And so the total number of times the inner loop runs, and this is the total, is just the sum of these. Right? So it's the sum. Okay, so it's n plus n minus 1 all the way going up to 1. This thing has a name. No, sigma is the name of that thing. Yes, you're right. Sigma is, yes, that letter is sigma. But this expression here, yes, it's a series. What kind of a series is it? It's not infinite. I just wrote down. Yeah? Never mind. It's not the Nevermind series, but yes. Geometric series. No, it's not a geometric series. Algebraic. Okay, so now like all the math terms will come out. Algebraic, geometric, trigonometric, inductive. Any others? Huh? Sorry? Binomial. Law of, yes. That's the sigma. But this series, it has a name. It's a particular kind of series. Yes. Linear series. I guess you. Yes. It's not a Taylor series. No. Yes. That's exactly what I'm asking you. That's factorial. Thank you. A round of applause, please. Thank you. It's an arithmetic series. You must have seen this, what, high school? Well, now you remember it. Okay. I'll rant about math education, but later. Let me first finish this. Okay, so I'm going to write this out as this is the summation of I, where I is going from 1 to n. Now, you already know what the answer is because you told me what it is, but for everybody, what is this? How much is this? Does that expression make sense? You're summing up I going from 1 to n. How much is it? N over 2, how much? How would you figure this out? I don't know. Like, this is even, like, it's harder to ask. I guess you could ask it on, you go to Math Overflow, right? And then you, right? Sure, and then you could count. But the for loop will only tell you what it is for exact values of n. But what if you need to know in general, yeah? Okay. The math education is coming back. It's buried in like deep recesses in your head. Yes, good. It's exact. It's n times n plus 1 over 2, which is why he said like the average, it's n. Like if you divide this by n, then it's about n over 2. Yes?
Maybe a more obvious way is to draw a graph.
Yes, I would. Yes, exactly. So this is O of n squared. But this is also omega n squared. Indeed, this is theta of n squared. The number of times the inner loop runs is theta of n squared, which means that actually for selection sort we have the theta bound. We know it's at most n squared, it's at least n squared. To see this, so there are, again, one way to see this is there is a formula for the arithmetic series, which is buried in your collective consciousness somewhere, but it's there. It's there. But another way to see this is to, here's just a plot that I'm going to draw. Okay, so you're summing up I going from 1 to n. So it's like, I'm going to mark out 1, 2, then I mark out 3, then I mark out 4, then I mark out 5, so on and so forth. Right? And if you see the area that I mark out, it's essentially half the square. Right? The area that I've sort of marked out is half the square. It's a little more than half because of the things above the diagonal, and hence it's an n plus 1 over 2. Actually, if you follow this, you can actually derive this exactly. Just count the area that's shaded. Right? It's going to be half, so it's that triangle, and then these little triangles. You add everything up, you'll get this expression. Pretty neat, huh? That's quite pretty. Okay, so the number of times that the inner loop runs is O of n squared, and it's at least n squared, it's theta of n squared. So T of n, the running time of selection sort, is theta of n squared. Okay? Yes?
Is there a big O notation for the best case scenario, or no?
Good. So big, as I said, like big O and omega just talk about functions. So you can talk about any function. Sometimes people will talk about the average runtime. But usually when you see it in the analysis of algorithms, it's often the worst case time. If people don't tell you what it is, it's the worst case time. Okay. All right, so is that clear? This argument, the upper bound, the lower bound, it's theta of n squared. Right? So hopefully even those of you who've seen, who know that it's n squared, at least understand it a little better. Like you see exactly why all the arguments. So you'll see, again, when someone says it's O of n squared, you can tell them it's theta of n squared. It's not just at most, it's at least n squared. In the worst case, it actually does run for some constant times n squared operations. Now what is interesting about selection sort is that you see this part here does not depend on the input. For all inputs, this loop is going to run because it has to find the minimum, so it just goes through everything. Good. So for this algorithm, exactly. The best case, the worst case, the average, they're all the same. Actually, the running time doesn't depend on the actual input, only depends on the size. Now, technically, you have slight differences between if this min doesn't happen, it might do this operation or not. So there are slight differences, but they're all, no matter what input you run on, it's theta n squared for all inputs. Okay? Now, for insertion sort, the picture is sort of different. So let's go to insertion sort now. And let's try to do sort of the same logic over here. Okay? So how many times the inner loop runs for insertion? Sorry, everyone following what's going on? Okay. How many times does this loop run? So I'm going to write this out. So here's the code here. So this is I, where I is that outer variable. So again, here also you have two nested loops. So I'm not going to write this out, but again, you can say it's O of n squared. Because the outer loop runs for n, the inner loop runs at most n. And the same logic works. Okay. So number of times. So for I want you to tell me what the answer is. Is it n minus I? Is it I? Or is it neither of these? Think carefully. How many times does the inner loop run for insertion sort? Is it n minus I, or is it neither of these? So I'll pause and I'll let you think about it. Remember, here's the code. Okay, so what is the answer? So, okay, so most of you got it wrong. It's a trick question, or it's not that tricky. So, someone who said green, why? Someone who had green, yes?
It depends whether you find it right away or later.
Exactly. It depends. It depends on what the input is, right? So, unlike, sorry, yes? Huh? It's a good question. Even in the worst case, it's not exactly I. No. So, okay. So good. So, maybe my question was ambiguously put. So I just said how many times. I didn't say exact. I didn't say for the worst case. Usually, what happens is if you you compute bounds on this quantity, and from there you get the worst case. So let me write what I'm saying, and hopefully then it'll make sense what I'm trying to say. Okay, so the distinction between selection sort is that this loop always runs for n minus I times. It always runs, regardless of the input. Here it runs for at most. So it runs for at most I times. Okay, the reason why I'm saying this is using this table and this way of thinking, you can only get a big O bound. Like if you just look at the number of times this loop runs, and you want to bound it without thinking about the input. So what you get over here is that for whatever, so I guess when it's 0, this runs 0 times. When it's 1, it's 1. And finally it's n minus 1, it's n minus 1. But this is at most. And so what you get from this is t of n is sort of, it's at most O of the summation of I going from 1 to n minus 1 of I, which is O of n squared. So, sorry, if I haven't been clear, my point is the running time, the number of times, depends on what the input is. There exist inputs where the number of times is always just 1. What is such an input? Yeah, in the back. Already sorted list, this loop will just, it's just going to exit at the very first step. So actually, technically it's 0. Like this operation runs once. But exactly, you're right. So when it's already sorted, this loop will, run 0, or I guess I consider it once because it has to make that comparison. So how do you argue that t of n is omega n squared? Maybe that's what you were saying. How do you argue that t of n is omega n squared? Does this make sense? So what you get by doing this analysis is you know that it runs at most I times. The at most is an O bound. But if you want the omega bound, the way that we did here, for selection sort, we could pin it down exactly. We know exactly how many times each loop runs. But for insertion sort, we just know it's at most something. And also, what makes insertion sort more complicated to think about is there are examples where insertion sort runs in O of n time. If the list is already sorted, so if A is sorted, then insertion sort runs in O of n time. Just to be clear, when I say O or omega, I could be talking about any function. In this case, I'm talking about the running time of sort when A is sorted, right? So this O always doesn't mean worst case or best case or anything. It depends on the context in which you write it. Without any context, it's usually the worst case running time. Am I making sense here? Sorry, the reason I'm going on and on about this is because there are lots of misconceptions. I want to make sure that you understand exactly what someone says when they say O of n or O of n squared. Okay, so how do you show that it's omega n squared? Yeah?
Could you try to find the best cases for each I?
Sorry, find the?
Find the best case for each I?
Or like the largest case for each I.
I guess, yeah.
The largest. Because the best would be sort of, yeah. So you want, yeah, exactly. So you need to find an input where things are really bad. So sometimes the omega bounds are trickier for that reason. So you need to find an input where instead of this being at most I, it's going to be I or maybe close to I. Yeah, someone, yeah? Yes, yes. A completely reversed list, exactly. So if the list was completely reversed, okay, so I'll write this down. This is important. Suppose A is sorted in decreasing order. Or you can even be more specific. You can say, suppose A is the input n minus 1, n minus 2, n minus 3, going all the way up to 0. Or actually, I don't think I'll get an off by one error here. So let me write it as n minus 1, n minus 2, going all the way up to 1. So suppose your list, the array was actually in decreasing order. In this case, in the ith iteration of the outer loop, right, so you're looking at the ith iteration of the outer loop, what is the value of AI when you start? In the ith iteration of the outer loop, what's the value of AI? Sorry? Go for it. J? No, but what is the value of AI in this array? It's n minus I, right? Because when initially in the ith iteration of the outer loop, I is 0, so the value of AI is just whatever the value of AI is, right? So the value of AI is n minus I. So let's look at what this list looks like at that point. Over here, you have n minus I. What does the list look like before? It's all elements up to n minus I that have been sorted. So it's going to look like n minus I plus 1, n minus I plus 2, going all the way up to n. Sorry, this is badly written, but right? So this is sorted. Which means that this element has to move all the way there. Right? AI, or the value at AI, has to move to the beginning of the array. Right? Each inner loop moves the value by one index, right? Because you're just swapping. So the inner loop must run at least, and this is the important thing, because it can only move by 1. So it has to run at least, well, technically it's like I minus 1 times. Right, because in every, once it, am I getting an off by 1 error here? It might be exactly I, right? So yeah, so, but at least I is also at least I minus 1, right? So, yeah.
Why do we say at least if that'd be the beginning of the array? Couldn't we not go more than I times? Since we're going back to the beginning.
No, so this element has to move all the way to the beginning in that inner loop. At each step, it's going to move by 1, which means that inner loop, whatever that loop is, has to run at least I times to move the element n minus I all the way to the beginning. Sort of, kind of. So the inner loop must run at least I times for this input. So the total number of times the inner loop runs is at least summation of I going from, I guess technically it's 0 to n minus 1 of I. Okay? And if you work this out, you'll actually get this as n minus 1, which is omega n squared. So to prove, so T of n, this is insertion sort. Is omega n squared. This argument is more complicated than just the O bound, because you actually have to find an input where things will be the worst case. Does that make sense? conventionally, you are not going to be expected to do this. I'm not going to expect you to do this in the course. So, but, well, it's important to know it, right? So that's what it means to say that it's omega n squared. It means that there exists an input where the running time is at least n squared. So I want to write out one last statement before I give you a short break. I'm just going to write this out over here. Again, this is like sort of the summary of what I'm saying. So what does it mean when I say T of n is O of n squared? This means, this is equivalent to saying, this is saying for all, which is, I'm putting this quantifier here, for all arrays of length n, the running time is at most Cn squared, and this is some constant. When I say T of n is omega n squared, then I'm saying that there exists, so that's the existential quantifier, there exists an array of length n where the running time is at least C prime n squared, where again this is some constant, it's some other constant. Like C and C prime are just constants. But this is important. So there's sort of a deep semantic difference between saying O and omega. O means that for all inputs it's running at most n squared. Omega means there exists an input where it runs at least n squared. Right? So you can't mix them up. Omega n squared does not mean for all arrays of length n it runs for at least n squared. For selection sort, that's actually true, that for all arrays it runs for omega n squared. For insertion sort, there's only, well, there is some subset of arrays. But this difference in the quantifier, is this notation clear? Like it's not an A, that's the other way around, right? It's the universal quantifier, and this is the existential quantifier. And so there's a difference between saying O and omega when you're talking about worst case runtime. Okay, so let's take a break for a few minutes, and then when we come back, we'll talk more about the notation. Hey. Uh-huh.
Just because, I finished like a week ago, and like all the tests were like pretty good. My output file matched.
We're pretty what?
Like my output file was matching.
Yeah.
And then like it said like it couldn't find a trajectory on the autograder, so it gave me like a 3. I don't know. I was just curious. Is that
wait.
something that can like
Okay, so I will give instructions on what to do about the homework. So for those of you who have few points, and usually there is a test case that failed. There is a log file that says something. What I don't let you do is I don't let you actually modify the code in that box because that's your submission. So what you should do is just copy the code to another container. You can just put it in like the hello world one. Copy the code somewhere else, experiment there, figure it out, and then do it. The reason I don't let you change this is because, well, someone might change it and then say, look, it was correct, right? And then once you show the TA or you show me what the problem is, we'll open it up, we'll let you fix it, and we'll regrade. For the first, I might not even have a penalty, or I'll make some call. Like if it's just some simple IO error, like you forgot a new line, you forgot to put something, you'll get all points. If it's a more significant error, we'll dock 1 point for the regrade. Okay? But the thing that always worries me is did my script fail? So I don't think it failed because a bunch of you did get 10, so clearly something is running. Okay, so where we were was this. Okay, right? So O of n square means for all arrays of length n, the running time is at most n square. Omega n square is there exists an array of length n where the running time is at least n square. So there is a difference between the omega and the O notation. Conventionally, people will, if you ever are at an interview and someone asks you a question, they're usually asking for an O bound. I think if you give them the omega bound, then you basically knock it out of the park, right? So what they're usually looking for is an O bound. Okay. So now that we have this notion of efficiency and running time, we can revisit our data structures, and we can ask for every data structure and every operation, what is the worst case running time? Write it down like O or theta notation, and then try to improve it. And that's how one comes up with better data structures. So let's build this table, which I call data structure versus an operation. Okay, so the data structure is listed here. And I'm going to write down the runtime for 3 simple fundamental operations: find, insert, delete. So just think of this as this is the list ADT, meaning the specification is that of a list. I just want to have a list of numbers where I find, insert, and delete. And I'll just write this over here, delete with pointer. I'll explain what that is in a minute. So I have these 3. And what I'm going to do is first, the simple data structure is the linked list, but maybe an even simpler one is an unsorted array, and a more complicated one is sorted array. So you're storing a bunch of numbers as a linked list. You could store as an unsorted array. You can store as a sorted array. So let's begin with the linked list. And as we discussed, for find, it's theta of n. Right? So finding is theta of n. Inserting is theta of 1. Theta of 1 is like O of 1 because it's always omega of 1. What that means is that the number of operations does not depend on the length of the list. It's like 4 or 5 operations. Now delete, I'm going to say with the appropriate pointers. What this means is for delete, if you had a pointer to the element and a pointer to the previous, then you can just delete an O of 1. Right? You just have to skip over the node. And to find the pointers is usually what takes n time. So I want to only look at the time that it takes to remove something, assuming you can find the pointers for it. So this is also O of 1. So n, 1, 1. So what that means in a linked list, you optimize the insert and deletes at the cost of the find. Now, in an unsorted array, how long does it take to find something? Yeah? So you have an unsorted array and you want to find an element. So O of 1 means that you can find it in time that is independent of the size of the array. No, find is like, find in terms of linked list. It's not access. What you're saying is access. Yeah. It's n because you just have to loop over the whole list. It's a loop over the array. So find is like, okay, so I guess there's a difference between find and access. Access is like, give me the ith element. Whereas find is like, find this value in the list. So again, it's theta of n because it's exactly, the argument is the same as a list. It's a for loop versus a traversal of the list. What about insert? Because you just insert at the end of the list. What about delete? So what do I mean by pointer? So here's an unsorted array. And I give you the index, and I say delete the element over there. Think a little carefully. Think carefully and then answer. I'll give you a moment. So you want to delete the element. You're storing an unsorted array of elements. You're storing a bunch of elements as an unsorted array. Yeah? Okay, like, that depends on how you implement things under the hood. But yeah, I don't care. Like, you need to get rid of this element so that whatever you have left is going to be an unsorted array of everything else. Does that make sense? You have to be careful if you insert white space, like if you put a 0 there, but now you've inserted something into the list. Unless you say, I'm going to put something that says null. Yeah?
Can we mess with the order of the list?
Sure, it's unsorted.
Okay, sure. So I just take the one at the end and then I go.
You just swap with the end.
Yeah, so then I don't have to shift all the.
You don't have to shift. Right? So all you do is you swap with the end and then decrement the size of what you're maintaining. Okay? So you can also do this in theta of 1. So I'll just write a little bit about what this is. So in an unsorted array, let's keep track of the size. So size is the number of elements that I'm storing in the list. To delete, swap, so this is ai with a of size minus 1, and then decrement the size. Yes? Yeah, so yes, you do have issues. You have memory issues which I don't want to get into. Let's assume that you've allocated enough memory to start off with. Sorry? Like a vector, exactly, which is basically an array where you dynamically change the size periodically. Yeah. Okay, so the trade-off for all of these things is, what about inserting an assorted array? The insert now is going to be theta of n, because if the array is sorted, and I insert in here, then I have to shift everything. And the delete is also theta of n. So the names for the theta of n is, this is called linear time. And this is called constant time. Yeah?
Wouldn't the delete just be the exact same thing as the insorted array? Because
why not? Yeah, exactly. Whereas if it's unsorted, you don't have to shift. So even though this looks like a dumb data structure, there's actually a benefit because certain operations are fast. Yes?
when people say constant or linear time, they're referring to theta of n, not O of n.
It's a good question. Usually they're referring to O. Usually they're saying O, but I think that if you say something is O of n, that's a bit ambiguous because it could also be O of 1. I could just replace all of these by O of n's and say this is correct, right? Which it is correct, because if it's O of 1, it's also O of n. So usually it's confusing. Sometimes what they're actually thinking is theta, but they're saying O, or vice versa. Yes?
Why are we using theta for this table and not O or omega?
Because I want to give precise bounds for each operation. When I say theta, I mean both O and omega. So if you replace all of the thetas by O, it's still correct. If you replace all of the thetas by omega, it's still correct. Whereas if I only wrote O's, I don't know what the lower bound is. I don't know actually whether. So if I said linked list insert is O of n, that is a correct statement, because O of 1 is like less than O of n. But I cannot say that insert is theta of n. That is incorrect. Is that clear? Yes?
So what if the O and the omega don't match? Is it possible to not have a theta?
So that means that we haven't figured out the theta bound yet. That's on us as the people analyzing that. We still haven't understood what the algorithm is. If we say, well, and this happens for algorithms, we say that, oh, the best O bound is this and the best omega bound is this, and we're not sure what it is exactly. But I don't think in this course you're going to see any algorithms of that form. So for all of these, we can pin it down exactly. So the reason for the sorted array is because this becomes an interesting bound, is that here we can actually get log base 2 of n. And this is by something that maybe many of you know. It's called binary search. So this is what, I mean, we only have 5 minutes left, so I'm not going to show you binary search in the analysis. But what I would like to do is to tell you what binary search is, which you're probably familiar with, and analyze it and prove to you that it's actually log n. Okay? And I'm just going to give the O bound. The omega is a little bit, and it's about the same thing. But so this, I hope this table makes sense. But this table is really important because this kind of tells you how to think about data structures. It's not that one is obviously better than the other. It depends on which operations you need to perform. So if it turns out that you basically just need to insert and delete, and you have to do a find at the end of the day, you might want to do an unsorted array or a linked list. But if it turns out you have to do lots of find operations, then you might want to sort, but the inserts and deletes become expensive. So these are called trade-offs. You trade off one operation over the other. And at least in the study of data structures, the ultimate is to get like a log n everywhere or an O of 1 everywhere. So we'll see, like in hash tables, you can actually get all of those to be theta of 1. Or in special kinds of binary search trees, you can get all of them to be theta of log n. Right? So that's going to be the next part of the course, like from the next few lectures onwards, is to try to understand data structures where we can make as many of those as log n with giving even more operations. And the reason I wanted to tell you about O and omega is then you can start appreciating these new data structures. Because you realize that, oh, this operation can be made faster, and this operation can be made faster. So just to give you some context for what we're doing next is, once we have these data structures done, the next stage would be to try to use the data structures for a problem by recognizing which operation my problem needs. Does that make sense? So that's what, so hopefully this, again, if you're getting hung up a lot about the limits of O, the limits are only there to define what O and omega are. But what's important is to understand like this picture here, this, like what does it mean to say O, what does it mean to say omega, and what does this table mean? So again, I'll summarize what I did today. I want you to make sure that you understand this logic over here. The theta of n squared for insertion and selection sort. This is important to know. And then to understand the difference between the O and the omega, and then this table of data structure operations. Next lecture, we'll do